Welcome back, folks. We're going to find node voltages, non-reference node voltages, using nodal analysis for the first time. Okay? Kind of structured similar to mesh, but everything's a little bit backwards. So the lecture is going to kind of take on pretty much the same format as I did when I introduced mesh analysis. The only difference is I haven't worked this problem before. I haven't worked this problem using the seat of the pants method. Maybe once I flip it onto the screen, you want to pause the video, try to work it using the seat of the pants method. Totally possible to do it. Give it a try if you want. But I'm going to use it to find node voltages. Maybe you're just going to have to take my word that we got the right answer and that it's consistent with if we had found it using some other method. Maybe you could use mesh analysis to validate. That might be kind of fun. Maybe we'll do that. Okay, so we're starting off with some steps for nodal analysis. These are the bare bones steps. I'll do the same thing at the end of nodal analysis, at the very end of the nodal analysis section. I'll have a strategy sheet. Okay, it's probably on the website. I'll make sure that I review it just like I did last time. I'll review it here for you. Okay, that'll be complete. But these are the steps that we begin with for our first problem. Label the non-reference nodes and a current direction for each passive element. Okay, so we just got to define the coordinate system. We got to say these are our unknowns, and then we're going to use these arrows to keep us honest with the science. Get our pluses and minuses correct every time. Then we're going to write a KCL equation for each non-reference node. Okay, so already that's different from mesh, right? We wrote a KVL for every mesh. Now we're writing a KCL for every non-reference node. Those are currents. We're looking for voltages, so we've got to kind of convert between them, and the way we do that is with Ohm's law. So we got KCL, we've got Ohm's law, and we already practiced that in the previous video, so we know how to write those equations, so we're good to go there. After that, it's algebra, and if we do the algebra and we don't screw up the algebra, we can get it into a system of linear equations. Okay, so if I have some set of unknowns, I'm going to have the same number of equations, and we can solve that system, and that's going to tell us what our node voltages are. Okay, so here's your toy problem. It's right there. We're going to find I out, this current here, using nodal analysis. Okay, so pause the video, do it by the seat of the pants if you want to, and see if you can't figure out what that current is. What I'm going to do is do nodal analysis and hopefully check the answer that you just got after you unpause the video, if you choose to. I think it's a good exercise. Okay, so the first thing we do is label our non-reference nodes. Okay, so ground is here, and that's 0 volts. Okay, so here's a non-reference node, here's a non-reference node, and here's a non-reference node, and we give them names. Okay, you can call them whatever you want. I tend to use letters when I'm doing nodal analysis, and I tend to use numbers when I'm doing mesh analysis. I'm not sure why. It's probably, if I dig back into my notes as an undergrad, I can probably find that. Okay, now every passive component gets a current direction. Just like we did in mesh analysis, we got to label our polarities. Here's the thing with nodal analysis. Pick a direction. Do not overthink it, and go with it, because really we're just trying to get the sign in the KCL to match the order of the terms when we use the KVL and Ohm's law to rewrite the equations. So I usually ask everybody, I should get a coin and flip it. Okay, I usually say left or right. Okay, and I have all of you pick it because it does not matter. It does not matter which direction you pick. When I have a current labeled, I usually try to keep it in the same direction. We got left or right, so let's go left in this case, and then I would say up or down, and well, that one was down. Let's make this one up. Okay, I already put too much thought into it. Honestly, my habit is go right and down. Everything goes right and down, and I don't think about it. I'll show you why this is all the case in a moment. Okay, now for each non-reference node, I'm going to write a KCL. Okay, so let's start with the KCL for node A. All right, I've got two components connected to it, so I'm going to have two terms in my KCL. The 6 amp is flowing in, so that's going to be plus IS. Okay, this one's leaving, and here's the first sign that's important. I'm writing the KCL for A, and this current is leaving A. So it's going to be negative, and I can say IR1, since it's the current through R1. Those are all of the things connected to node A, so Kirchhoff told us that that's going to be equal to 0. Okay, IS is a constant. IR1, if I was going to write the expression for this current, like we did a few videos ago, I would say what's the voltage at the tail minus the voltage at the tip, and I'm going to divide by the resistance. And stop and check yourself. This is a voltage, this is a resistance. Divide those, and I'm going to get a current. Okay, so we'll just make sure the units are the right units. Okay, so when I have that, I can plug it in there, right? Plug that in there. So IS can come down. The negative sign comes down. Okay, so that negative sign comes from the KCL. IR1 itself is what I have written here. VA minus VB over R1. And that's equal to 0. Okay, that's close to my equation. I want a system. I want an equation that I can put into a linear system in matrix form. So I've got to do a little bit of rearranging. This is a constant. I'm going to bring that over to the other side. When I break up this fraction, just make sure you know how to break up fractions and do it correctly. R1 is going to be in the denominator on both of them. I see some creative algebra there sometimes. Okay, so, and the negative sign is going to distribute. Okay, so that negative sign distributes to both terms. So I can rewrite this as negative 1 over R1 times VA plus 1 over R1 times VB. And then if I bring IS over, it's going to be negative IS. Okay, there's my first equation for this system. I just got to plug in some values. So what's R1 here? We got 2. Okay, I think I can handle that. So I'm going to get negative 1/2 in front of VA, positive 1/2 in front of VB, and IS is 6, so this is going to be negative 6. Okay, so there's my first equation for my system. That was the KCL for A. We just do the same thing for B, and we do the same thing for C. Put it in a system and solve it. So let's keep rolling here. I'll sneak this one over here. KCL for B. It doesn't matter which order you do them in, as long as you get them right. Okay. So I've got 1, 2, 3 terms because I have 3 things connected to the B node. Looking at this current, now it's entering B, right? So it's going to be positive. So it's going to be positive IR1. This one's leaving, so it's going to be minus IR2. And this one's entering, so it's going to be positive IR3. That's all of them. Kirchhoff says that's equal to 0. Okay, let me scroll down a skosh. I think we should all petition to have skosh added as a SI unit. Totally do. Okay. IR1, well, we already had it. Look, hey, we got that expression up here. And as long as I'm using the same arrow, I'm going to be okay. But let's write it out anyhow. IR1 is equal to VA minus VB over R1. Let's see how much I can, well, I think I can fit it all in. IR2 is equal to, let's see, where's R2? There it is. VB minus 0 over R2. Okay, which of course is just VB over R2. All right, where's the last one? IR3, so it's going to be VC minus VB over R3. Okay, so I got to scroll off the screen, sorry about that. VC minus VB over R3. All of these images should be posted. That's not, well, I'm sure it's equal to something, but it's good the way it is for me. All of these images are posted, right? So if I ever have to scroll around, I'm hoping that you can just open the image. You have the worked problem after I finish the video. you can follow along there if you need to. Okay, so now we've got to plug all of these in, right? The algebra gets a little sloppier with this. The positive sign comes down. I'm just going to ignore it. And we plug in IR1, VA minus VB over R1. The negative sign comes down. We plug in IR2, which is over here, VB over R2. The positive sign comes down. And we plug in IR3, VC minus VB over R3. And that's equal to 0. Okay, so we're almost there. We just got to do a little bit of algebra. Okay, so we're going to break up the fractions. So I'll do this in a few steps just so we don't get lost. 1 over R1 in front of VA minus 1 over R1 in front of VB. Minus 1 over R2 in front of VB plus 1 over R3 in front of VC minus 1 over R3 in front of VB. Okay, so just double check myself, and that's equal to 0. Okay, collect like terms. So my habit again is to just make it positive and throw a parenthesis in there and then say, okay, where are all my VA terms? Well, here's VA. Okay, so it's just going to be 1 over R1 in front of VA. That one just has 1. So I'm going to make this positive, throw a parenthesis in there. Where are all of my VB terms? So here's VB, VB, and VB. Oh, there's a lot going on there. Okay. And we get negative 1 over R1, negative 1 over R2, and negative 1 over R3. And that's in front of VB. Okay, make the next one positive. Throw a parenthesis in there. And where are the VCs? Here it is. Okay, the only thing there is 1 over R3, and it's positive. And that's in front of VC. That's all equal to 0. Okay, I like this format better. All of our coefficients are gathered together. It's going to be closer to ready to plug into whatever calculator you're using. MATLAB and probably Python allow you to be a little sloppier with that if you choose to be. Okay. Whew. The first problem always takes the longest, right? Hold on to your seats here. Okay, now we plug in values. So I'm looking, I got the problem over here on my other screen, so I can pick off the values. I'm hoping you have the image if you want to be looking at the image while you're watching the video. Okay, so 1 over R1 is 1/2 in front of VA. So now I have negative 1/2, negative 1/4, and negative 1/4, which makes negative 1. Okay, so it's just going to be negative VB as I plug that in. Okay, R3, so I'm going to have plus 1/4 in front of VC, and that's equal to 0. All right, that looks good. Bunch of constants. And the unknown node voltages, nothing else. Just like we talked about in mesh. Guess what's going to happen when we get dependent supplies? Same game, different name. Okay, so let's see here. Let me just check myself quick, because if I made a mistake, I want to fix it now. No, we're good. We're doing great. Great. Okay, so let's see here. Negative 1/2. Yeah, oh yeah, we're good. Okay, so we've got the KCL for A and the KCL for B. We got to write the last one for C, and there's only 2 things connected to it. All right, so let's sneak it in down here as much as we can and say the KCL for C. Let's see, this current's leaving, so it's going to be minus IR3. This current's entering, so it's going to be plus IR4. Those are the only 2, so it's equal to 0. I bet that's behind my head. Not quite. Cool. All right, buddy. Okay, IR3. Let's see, it's going to be VC minus VB over R3, right, voltage at the tail minus voltage at the tip, over the resistance. And then over here we're going to have IR4, and I am going to write that behind myself, so let me disappear. IR4 is equal to 0, right, because the arrow's going up now, so the voltage at the tail is 0, minus the voltage at the tip, which is VC over R4. Okay, so that would be negative VC over R4. Okay, and we just got to plug those in and do some rearranging. I think I'm going to copy that and slide it down because I'm kind of pushing the limits of organization here, which is true if you've ever, it's my favorite hobby. All you have to do is look at my office. I kind of like having the green screen. You can't see what's around me. Okay, so I just got to plug these in. Okay, so let's see. The negative sign drops down, and I plug all of this in. VC minus VB over R3. The positive sign drops down from the KCL, and I plug this in. Okay, so here's the plus, and I get negative VC over R4. Okay, so getting that sign and this sign to match correctly is why we draw the arrows. That's the important thing. Okay, and that's equal to 0 from the equation we wrote up here. Breaking up the fractions, we get negative 1 over R3 VC plus 1 over R3 VB, right, because that negative sign distributes. And then we get negative 1 over R4 VC, and that's equal to 0. All right, so a little bit more algebra, grouping like terms. We've only got VB and VC. Okay, so we're going to look for our VB term, which is here, and we have 1 over R3 in front of VB plus, and then we have some VC terms here, and we get negative 1 over R3 and negative 1 over R4. That's in front of VC, and the 0 drops down. Okay, same algebra. I can make you do it quicker. We'll get there. We'll get there. Okay, plug in some values. Let me get the circuit here again. Plug in some values. Where is it? As I scroll through my notes, you can't see what I'm doing. Sorry. Okay, so we're going to have 1 over R4. I'm sorry, 1 over R3 is 1 over 4 in front of VB. And then looking at R3 and R4, we're going to have negative, it's going to end up reducing to 3/4 in front of VC. That's just plugging in the values of R3 and R4, and that's equal to 0. And look at that. A bunch of constants and our unknowns. So we're good to go with that. Okay. So let's gather these up. Doesn't matter the order that you put them in. You can swap rows all you want. But that was one of our equations. I don't even know which equation is which anymore. But I'm just making copies of these so I can grab them down here. And, you know, maybe let's do this. Let's rearrange this a little. Let's put them over here. Okay. Just so I can get my matrix form down in the bottom here. Okay. Get that up as high as I can. All we got to do now is solve this. Oh, we got to find I out too. You got to remember what the original question was. We got to find I out. Okay, so it doesn't matter the order you take them in. So let's take this one first up here. I can't remember which KCL that was, but we take the coefficient of VA, we take the coefficient of VB, and we take the coefficient of VC. Okay, and the right-hand side, of course, is 0. Remember that you're inverting the matrix. If you don't write that, it's not mathematically correct. Okay, let's come down here and take this one. So we take the coefficient of VA, the coefficient of VB, and the coefficient of VC, be careful, there is no VC, right? And that's a 0, and the right-hand side is -6. Looking at this one, okay, right off the bat, be careful, there's no VA, so you might be moving quick and not paying attention. Stop and say to yourself, what is the coefficient of VA? It's 0, because we don't have a VA term. 1/4 in front of VB, and -3/4 in front of VC. Right hand side is 0. Okay, that's going to correspond to the order of the coefficients, and that's how we're going to get the order of the unknowns that pop out of this thing. Okay, I'm reaching for my calculator in about 5 seconds here. You should be too. Just practice plugging them in. The fractions become a little bit of a pain, so that's why I think it's worth practicing this with your calculator as well. So I got 0.5, -1, and 0.25. That was easy for me since I did them in decimal, which is fine. -0.5, just get it right. 0.50, -6, 0, 0.25, -0.75, and 0. All right, and from that, I get node voltages of 26.4 volts, 14.4 volts, and then 4.8 volts. Okay, now I know my node voltages. I'll roll out of the way there for you. I know my node voltages. I can go find any other value in the circuit, but what I wanted to find was I out. So I'm going to scroll back up and look at that because I don't think I have room to copy the circuit again. There it is. So there's I out. You've already written an equation for I out because it's the same thing as IR2. So we just got to find that one. It's going to be the one connected to B. It's right there. Voltage at the tail minus voltage at the tip over the resistance. So we're writing it in the same way. Okay, so let's go. I think I have a little blank space in here. Let's use that. Okay, it's going to be, well, I don't know. I'll go down the bottom. VB minus 0 over 4. That's all it is. Okay, so if we say I out equals VB minus 0 over R2. I think it's 2. Sorry, scrolling again. R2, which is value 4. Okay. Well, look, now I know VB, right? It's 14.4 minus 0. Kind of feels silly writing that, but there it is. Over 4. All right, so grab your calculator. Take VB and divide it by 4. So it's going to be 3.6 amps. Okay? Find the node voltages. Use them to find any value in the circuit. That's our goal here. Okay, this was our first problem. I've got to make it more complicated. There's a couple wrinkles that we're going to throw here and there. We can do nodal analysis with multiple sources, all of the same good stuff that we could do with mesh, but we've got to make it more complicated, and that's what I'm going to do. Okay, so stay tuned and good luck.